Hello, this addendum is Hello, this addendum is about impedance matching, addendum 2b, chapter 2, and we are talking here about ways to match the load impedance to the source impedance. In the main chapter, we discussed that matching is important to prevent multiple reflections and therefore to enhance the quality of the transmission of the signal, and hence to enhance the transmission and hence enhance the signal transmission through the transmission line. The basic idea is that you have a load impedance that is not matched to the source impedance. Typically, the source impedance is resistive. That's the typical situation in high frequency applications. So what we would like to do is present a matching network here to make the load impedance look like so the main idea is to insert design a network here. We'll call it the matching network that would present the source with a matching impedance here equal to that of the source impedance. There are so many ways there are different approaches to achieve that. Some of them is simply to add a series impedance or add a shunt impedance. A bit more sophisticated is to add what we call the L network or the pi network or the T network. Each one of these have its own advantages and it's a step towards a better each one of those has its own advantages. Like this one here, the advantage is the simplicity. Here although these schemes are good for however, these kind of schemes are not typically used in the transmission line network matching. However, these kind of schemes are not typically used in transmission line network matching. The typical schemes used are either the quarter wave, half wave transmission line matching scheme, or as we will see on the next slide, the stub matching scheme. So let's get to discuss those. So let's start by discussing the quarter wave, half wave scheme, and then we'll do next. So let's get to see how these work. Well, basically, the quarter wave matching scheme will work by designing a quarter wave transmission line whose characteristic impedance is basically the geometric mean of the two impedances. If you recall, for a quarter wave transmission line, the input impedance is Z0 squared over R sub or. If you recall, the characteristic impedance, if you recall, for a quarter wave line, the input impedance is equal to Z0 squared over ZL. So choosing a choosing a line whose Z0 is equal to the square root of the product of these two, like this expression here, will lead to impedance matching here. So the input impedance here will equal to R sub S, and in fact also the output impedance looking from the load side will equal to R sub L. The reason we're using R's here is that typically we want to use a lossless line here, so the characteristic impedance here has to be real, and for this to be real, obviously we are talking about real impedances here as well. So this kind of scheme would work when everything is real. If these are complex, to have a geometric mean as complex, that means we have to design a special transmission line with complex characteristic impedance, which could be lossy, and that's not really desirable. The half-wave transmission line, basically, for the half-wave transmission line, basically the expression is Z input is equal to ZL. So this kind of scheme will not work for general impedances here that are not matched. Here we are talking about matched impedances that for some reason we have to insert a separation. And in this case, the optimum length for that separation is half a wavelength. In this case, you always have matched impedances. In this way, you always have matched impedances. Looking from here, you see Z0, which is equal to ZL, and looking from here also you see Z0 is equal to ZL. Let's get to the stub matching, which is a typical scheme used in the general case. As you can see that these kind of schemes here will work in some special cases. For the general case, they may not work. The stub matching scheme is the typical scheme used in the general case. Let's get to that. The stub matching scheme is the typical scheme used in the general case. So let's get to that. The stub matching scheme is basically, the stub matching scheme is about adding either a series or a shunt, short or open, the stub matching scheme is about adding a series or a shunt impedance somewhere on the line to eventually make the input impedance here match to the source. Somewhere on the line such that the stub matching scheme is about adding a series impedance or a shunt impedance at some location on the line to provide this matching. A series impedance is typically achieved by adding a short A series impedance stub is typically achieved by adding a transmission line in the series impedance scheme. The series impedance scheme is typically achieved by breaking the line at some location and adding a transmission line section at that location in a series connection format, while the shunt impedance is achieved through adding a shunt transmission line in parallel with the main transmission line at some location here. By choosing the location as well as the characteristic impedance and the length of the stub, we can achieve this matching condition, and we'll see how that works. The point is, you have a complex impedance here. So when I find the location on the line at which typically those transmission line or stubs are either terminated in a short circuit or an open circuit. We are showing only the short circuit here. The short circuit is preferred because it provides a definite. The short circuit here is preferred because the short circuit termination here is preferred because it presents a well-defined location. And an open circuit may be a short circuit is typically chosen preferred because of the ease of implementation, as well as also the short circuit is preferred because of the ease of the short circuit is preferred because of the ease of implementation. Typically the short circuit is preferred because of the ease of implementation. Another good reason is an open circuit will cause radiation here, which can cause losses, and that may reflect on the quality of the impedance match that we have. However, an open circuit termination can be designed as well. However, in some cases, an open circuit may be can be used as well. Now, if we were talking here about a short or open section of a transmission line, that means the input impedance to that section is reactance. That means the input impedance to this section here is reactive. So is this situation as well. So that's why we are labeling the input impedance here by JX, and we are labeling the inputs susceptance of the line, and we are labeling the input susceptance of this section of the line by JB. Now, being reactive here or there, that means being reactive here or there means what we are adding here is a reactance correction. That means the line by this location here must have already achieved the proper resistive matching. And all what we need is adding the reactance here to finish to complete the matching requirement. So if the resistive part at this location here is equal to R sub S, then all what's left now, if there is some reactance, we counter this reactance by the reactance of the added stub. Likewise here. So what we do is, starting with a ZL, we find the location on the line at which this is equal to R sub S. And that's what we are doing with this expression here. We're talking about the real part of the impedance at some location D is equal to R sub S. The real part of this is equal to R sub S. So what's left is to take care of the imaginary part of that by what? By adding the reactance of the stub. So the imaginary part of the input impedance, so the imaginary part of the driving point impedance at that location can be fixed by adding a series stub or by adding a shunt stub. By adding a series stub or by adding a shunt stub. So here are the two sets of So here are the corresponding equations to these two cases here. The top one here is for So for the series stub, the expressions are right here. This one and this one. The real part of the main line at this location must equal to R sub S, and the combination of the imaginary part plus the series reactance must equal to 0. That means the total impedance now is equal to R sub S. And we have matching. For the case of the shunt stub, at that location here, the location D, we're talking about the real part must be matched, while the imaginary part combined with the shunt susceptance must cancel to 0. Must cancel to 0. These expressions here are rewritten in that format here. However, solving such problem is much easier using the Smith chart. And actually the last example in addendum 2E goes through the process of designing a stub matching section for a transmission line. So that's why the recommendation here is to go to addendum 2E of the Smith chart and follow the steps there. It's very well explained in the procedure of the last example in that addendum. This concludes addendum 2B and I'll see you in another video.